All right, so one of the things we talked about last time was uh, we talked about these various processes. Isovolumetric process, a process where the volume is constant. And again, we're talking about gases here. So isovolumetric processes, here's the isovolumetric process. Volume is constant, isobaric process, pressure is constant, isothermal process, temperature is constant, okay? An adiabatic process where the system goes through a process without exchanging heat with the environment, absorbing or exchanging heat with the environment. So in an adiabatic process, if the gas expands, when a gas expands, it does work. Okay. So when it does work, where does the energy for doing work come from? Well, but you didn't absorb any heat. So you spent internal energy. Okay. So you spent money from your savings account. And if your internal energy, if you used some of your internal energy, your temperature decreased. So here's an adiabatic process where you went from a high temperature state to a low temperature state. Your internal energy decreased. Okay? So we talked about some of these processes. So again, in an adiabatic expansion, your temperature decreases, and in an adiabatic compression, your temperature would increase. Okay? So now we talked about all of that, and then we said something about each of these terms for those processes. This is the first law of thermodynamics. This is change in internal energy is equal to heat added minus the work done. Okay. And we said something about each of those processes, each of those terms in the processes. Okay, now we'll do we briefly talked about this actually in the last chapter, but what we're going to do is we're going to take a gas and we're going to warm it. Okay. So when you raise the temperature of the gas, okay, what is it that you're doing? You're speeding up every molecule. Okay, so when the temperature goes from 100 to 101 degrees Kelvin, let's say for this gas, the average kinetic energy of every molecule has increased from a certain amount to a fixed amount. Okay? Now let's do the following. Let's say we'll add the heat, so let's say this corresponds to 100 degree Kelvin, or let's choose a room temperature. This corresponds to 300 degree Kelvin, and this corresponds to 301 degree Kelvin. Okay? So we warmed up the gas from here to there along this path, and we warmed up the gas along here to there along this path. So no matter where you are on this path, on this curve, the average kinetic energy is the same because the temperature is the same. No matter where you are along this curve, the average kinetic energy is the same because the average kinetic energy just depends on the temperature. All right, so you have 100 molecules. You increased its energy from here to there. Okay, so the energy increase per molecule is the same whether you went along this path or along this path. The energy increase per molecule is the same. Now, if you go along this path or go along this path, where do you add more heat? So that's what this equation is telling you. The heat added is the internal energy increase. Okay? Internal energy increase is how much energy increase for each molecule, plus any work done in the process. Okay. So along this path, are you doing any work? When you're warming the gas along this path, are you doing any work? So we learned that for an isovolumetric process, the work done during a process is the area under that curve, and there's no air, the area under this curve is 0. The work done along this path is the area under that curve. So you do work on that path. Okay? So along this path, the work done is 0. All the heat added is just going into speeding up the molecules. Along this path, you're speeding up the molecules. In addition, you're doing work. So you're adding more heat. So, and this path is a constant pressure process. So the heat added along this path is heat added along a constant pressure. This is heat added along a constant volume. And the heat added along constant pressure is greater than heat added in a constant volume process. Okay? Because for a constant pressure process, you had to do work as well. Okay? Now we'll figure out how much more heat you need to add. Okay? And of course, are those the only two paths of raising the temperature from here to there? There's an infinite number of paths, okay? So, you know, for every path, the heat added is different. Okay? All right, so there's an infinite number of paths, ways of going from this temperature to that temperature, but we'll only consider these two paths, this path and that path, okay? All right, so so this is the heat added at constant pressure. This is the heat added at constant volume. This is the heat added along this path. This is the heat added along that path. We already know that we add more heat along this path. And what this equation says is the number of moles of gas you have times the molar specific heat at constant pressure times the rise in temperature. This is the same, this is the same, so this is greater than that. Okay? So the molar specific heat at constant pressure is greater than the molar specific heat at constant volume. Okay? And now we'll show you for an ideal gas that this turns out to be, as long as the gas is ideal, it doesn't matter what it is, this turns out to be equal to the gas constant. Okay? So that's what we'll show. All right, now before we do that, we'll derive CV. Again, we've done this before. Okay, so CV is, by the way, for gases, we define the molar specific heat. Gases, it's easier to measure how much gas you have in moles rather than mass. So that's why we define molar specific heats. Okay. All right. So let's do CV for a gas. Okay. Okay. Now the total internal energy of a gas is the number of molecules of the gas, and F is the number of degrees of freedom per molecule, and each degree of freedom contributes this much to the kinetic to the internal energy. So the total internal energy of a gas is N times F by 2 times K times T. Okay, and N, the number of molecules, is the number of moles times the Avogadro's number times F by 2 times KT. And the Avogadro's number times K is equal to R. So the internal energy of a gas is F N times F by 2 R T. This times that is R. Okay, so CV is defined as 1 over N D internal energy with respect to the temperature. Okay, so if you take this, so CV is 1 over N D by dt of N F by 2 RT. The N cancels, and this is equal to F by 2 R. All right, so CV for an ideal gas is F by 2R. F is the number of degrees of freedom of the molecule. Okay? So if you have a monoatomic gas, the number of degrees of freedom are 3, and CV is 3/2 R. For a diatomic molecule, the number of degrees of freedom are 5, and it would be, at room temperature, it would be 5/2. Okay? All right, now let's derive this equation. Okay? So we'll show that Cp is greater than Cv by R. Okay? All right. So here is the first law of thermodynamics. The first law of thermodynamics is Q minus W. So Q is increase in internal, the amount of heat added is rise in internal energy plus the work done. Okay, so dQ, if you add an infinitesimal amount of heat, it's equal to the infinitesimal amount of increase in internal energy plus the work done. Okay, if you add, now we're going to add heat at constant pressure. So that's the number of moles of gas you have times the Cp times delta T, the rise in temperature. Okay, internal energy rise is just from the molecule speeding up, and that's accounted for the specific heat at constant volume. So this is equal to that. And the work done by the gas is the pressure of the gas times the change in volume of the gas. Okay. Now, for an ideal gas, P delta V is equal to N, let's say PV equal to nRT. Okay, and if you're changing the volume, it's the temperature changes. Okay, so P delta V is nR delta T. Okay, and you can see that N and delta T are common. Okay, so we'll bring this on the other side. So N times Cp minus Cv delta T equal to nR delta T. Okay. So Cp minus Cv is equal to R. Okay. So for any ideal gas, the amount of heat added at constant pressure, the specific heat, molar specific heat at constant pressure, is greater than the molar specific heat at constant volume by R. Okay. All right, here's an important parameter we defined, gamma, which is the ratio of specific heats. Okay, and you'll see in a second what this will tell you. Okay, so here are some values. Okay, so here are various gases: monoatomic gases, diatomic gases, polyatomic gases. Okay, so these are the noble gases. There's the Cp and Cv, and experimentally measured Cp and Cv, and look at the difference. The value of R is 8.314 joules per mole per Kelvin. Okay, and you see all these values are right about there. Okay, so the experimental values agree with our theoretical prediction for a range of gases. Okay. And look at this, gamma, the ratio of specific heats, okay, is Cp over Cv. All right, so Cv is F by 2R. F is the number of degrees of freedom. Cp is Cv plus R equal to F by 2R plus R equal to F plus 2 over 2. So gamma equal to Cp by Cv is F plus 2 over F. All right, so gamma tells you the number of degrees of freedom a substance has. a gas has. Okay, and the more complex a gas molecule is, the more degrees of freedom it has. Greater the number of degrees of freedom, gamma tends to be 1. For an infinite number of degrees of freedom, this would be 1. So you see, for a monoatomic gas, that would be 3 plus 2, 5 by 3. Here's 5 by 3. For a diatomic gas, that's 5. 5 plus 2, 7. 7/5, which is that. And for a more complicated gas, as the number of degrees increases, this tends to become 1. This gets close to 1. Okay? So the closer gamma is to 1, that tells you the more complicated the molecule. Okay? So, all right, so here's a monoatomic gas. It has 3 degrees of freedom. This guy has 3 translational degrees of freedom, and these 2 rotational degrees of freedom. The rotational degree along the axis is not excited because the first excited level has too large an energy. Okay? And more complicated molecules, they'll always have 3 rotational degrees of freedom and then vibrational degrees of freedom. Okay. So CV, we saw that earlier, CV equal to F by 2R. F is the number of degrees of freedom for the molecule. So for a diatomic molecule at room temperatures, the 3 translational degrees of freedom are available, and these 2 rotational degrees of freedom are available. This is not available. Okay? To excite this level, this degree of freedom, to make it rotate along that axis, you would have to heat the gas to about 500,000 degree Kelvin. Okay? The first excited level is available only at those temperatures. What happens at those temperatures? What do you think will happen at those temperatures? What's that? This, you would split up the molecule. The molecule, you would destroy the molecule. So you never get to excite that, okay? All right, so at room temperature, this guy has 5 degrees of freedom. This would be 5, and that's 5 halves, okay? And Cp by Cv would be 1.4, okay? And that's what you see. So around these temperatures for all these diatomic molecules, gases, Cp by Cv is around 1.4. So this is for a hydrogen gas, I believe. Okay, so you see, so hydrogen is a diatomic molecule. Okay. At these temperatures, at 100 degree Kelvin, Cv is 3/2 R. So it has only 3 degrees of freedom. Even the rotational degrees of freedom are not excited. Okay. At these temperatures, the rotational degrees of freedom are excited, and Cv is 5/2 R. And at these temperatures, the vibrational degrees of freedom are excited, and Cv is 7/2 R. Okay, what does this mean? This means if you took the gas and tried to heat it at constant volume, okay, so let's say you took 1 mole of gas and tried to raise its temperature by 1 degree Kelvin. At these temperatures, all you need is 3/2 R amount of heat. At these temperatures, you need 5/2 R of heat to raise the temperature 1 degree. At these temperatures, it takes 7/2 R of heat. So it's taking different amounts of heat to warm the same gas by 1 degree Kelvin at different temperatures. That's what this graph is telling you. Did you guys understand that? Okay. So its properties are changing at different temperatures. Okay, it's not behaving the same way. Yeah. It's like saying, you know, when you're poor, your monthly expenses are $500 a month. You're middle class, your monthly expenses are $1,000. Okay, so that's when there are more degrees of freedom, it takes more heat to raise its temperature. All right, so now we'll say something about an adiabatic process. Okay, this is an isotherm. What does an isotherm mean? Yep. What does iso means constant, therm means temperature. The temperature is constant along that line. So the temperature of the gas is constant along that line, meaning its internal energy is not changing. All right, in physics, a lot of times you'll see a process, and what you want to do is say what is constant. So you like to say things are changing during a process, but there'll be something that is constant, and you want to say what is constant. So that's what we said. Along this process, temperature is constant. So there were all these processes, stuff was changing. Along this process, pressure was constant. In this process, temperature was changing, pressure was changing, but volume was constant. Okay, so that's what we want to be able to say. Okay, so here's an adiabatic process. In an adiabatic process, you're not absorbing heat or giving up heat. The system Q is 0. And the question is anything constant during this process? And it turns out that if you take the pressure of the gas, the volume of the gas to the power of gamma, we introduced gamma, this quantity is constant. It's a complicated looking quantity, but that quantity is constant at every point on that curve. So you can see that P and V are changing at every point on this trajectory, but if you take P times V to the power gamma, that'll be constant along that trajectory. Okay? So that's a interesting statement. Okay? And now let's prove that. We'll prove that. All right, so here's the first law of thermodynamics. This is the heat added. That's equal to change in internal energy plus the work done. Okay, now this is an adiabatic process, so you didn't add any heat, so that is 0. Okay. So any change in internal energy is equal to negative of the work done. So if the internal energy decreases, that means positive work was done. Okay, so if internal energy decreases, that is negative, so W has to be positive. Okay, any work done comes from the decrease in internal energy. Well, change in internal energy is N times CV dt. Okay, and any work done is equal to P times dV. Okay, so again, now we're dealing with an ideal gas, so PV equal to nRT. Okay, the change in this quantity arises from change in volume plus change in pressure. Okay, so this is the chain rule that you do in calculus. Okay, so any change in this guy arises from this change plus that change, and that's equal to nR del dt. All right, except that, so now for an adiabatic process, see, n dt is R times, so this is equal to n R times n dt, and n dt from here for an adiabatic process is PV minus P dV over CV. Okay, so we've written the right-hand side. So this is true for any process, but for an adiabatic process, this is equal to that. Okay. And that's equal to that. So what we have done is, this is the change in dV, this is another term of dV, and we'll collect them together. Okay. But first, R is Cp minus Cv. R is Cp minus Cv divided by Cv times P dV. Okay. And this is gamma and gamma, and that is 1. Okay, so, and there's a minus sign, so minus gamma plus 1 p dv. Okay, so this is equal to p dv plus v dp. All right, and one of these guys cancels. Okay, so v dp is minus gamma p dv. And now we'll bring the p down there and v down there. Okay, so for an adiabatic process, this is true. Any change in pressure divided by the pressure minus gamma times change in volume divided by volume. So logarithmic change of pressure is proportional to logarithmic change of volume. Okay. Now, if you have an equation, what we'll do is we'll integrate it. So whatever you do to the left-hand side, you're going to do to the right-hand side. What is integral dx over x? Okay, so this is log p equal to minus gamma log v, and we're doing indefinite integrals plus a constant. Okay, and so log p plus gamma log v equal to a constant. P, and this is v to the power gamma, v to the power gamma is a constant. Okay, and so raise both to the power e, so c, and e to the power log pv to the power gamma equal to e to the power constant. So pv to the gamma is some new constant. Okay, so that's what we've shown. All right. Anyway, don't worry about it if you didn't follow the derivation. So what's important is, okay, so in a process, in a thermodynamic process, what we want to show is, what we want to be able to say is, if some quantity is constant, along an isotherm, what is constant? Temperature is constant. Along an adiabatic process, it's not a single quantity that's constant, but this combination is constant. Okay? So that's a statement, and that's useful. Okay, and it turns out that so if the system consists of an ideal gas, you can use this equation, nRT, okay, and substitute in this equation. You showed that this is constant, meaning this combination at any point is equal to that combination at a different point. And so you can use this and show that TV to the power of gamma minus 1 is also constant. Okay. So these two are equivalent statements for ideal gases. Okay. All right. Now we're going to show you something else. We'll talk about something. So you guys know what is the density of air? What is the density of the atmosphere? So the density of air at sea level is about 1.3 kgs per meter cube. Okay. So again, this is a meter cube. This much air weighs 2.5 pounds. Okay. Now, if you go up, let's say we go up 1,000 feet, or let's go 5,000 feet, and you take this much air, at that height, does the air weigh the same? What happens? So the density decreases. And we want to see how the density decreases. And we'll see in a second that the density decreases exponentially. So here's an amazing fact. When we define space. When does space start? So space starts when it becomes sort of a vacuum. When does space start? Do you guys know the definition? So the rough definition is 100 kilometers, about 60 miles. Okay. Back in the days, around the time you guys were born, there was a prize for the first private company to get to space. This was just 20 years ago. The prize was $10 million. Okay, for the first private company to reach space. Anyway, so space starts around 60 miles, 100 kilometers. If you go 5 miles up, you have crossed half the atmosphere. The other half of the atmosphere is by weight. So what that means is, so what I'm saying is, so here is a column of air. So this is 60 miles. The first 5 miles weighs the same as the next 55 miles. Okay. Anyway, so the atmosphere decreases exponentially. Okay. So let me quickly go over this. Okay, so here's how the argument starts. By the way, so what is the ideal gas law? PV equal to nRT. Okay. So we'll write it like this. P equal to N over V RT. Okay. Now we'll assume something that's not true, but this is government work, so we'll let it slide. Okay. We'll assume that the temperature of the atmosphere is constant. Okay, as you rise up. All right. So here's the deal. So here's the question. Look at this slab of air. Okay. So let's look at the slab of air. The slab of air. Does this slab of air weigh anything? What's that? Yes, it weighs something. Okay. Does this weigh anything? I'll let go. It fell. Right? Why is this slab of air not falling? What's that?
The buoyant force, right, be pushing it out because there's air.
Why is there a buoyant force? It's got the same density as the surrounding air. There's no buoyant force. So, did you guys understand that? Did it get under your skin? No? No? All right. So, the only way to explain that is, okay, so this has a weight, so there must be a balancing force upward. And how's the balancing force coming? The pressure at the bottom must be greater than the pressure at the top. Okay? And the pressure at the top, okay, so let's look at this expression. So the pressure at the top is lower. The temperature is the same, we have assumed. So that must mean the density of gas is less at the top. Okay? So there are less molecules at the top that are hitting it less frequently. Okay? So that's what's going on. Okay? So as you go up, the density of air decreases. And that's what's holding this thing up. Okay? So this goes, here's the pressure at the bottom. Here's the pressure at the top. And so dP is negative. Okay? The change in pressure as you rise up, this is negative. Okay? This is the force at the bottom, force at the top. That's equal to the weight of this amount of gas. Okay? And so if you go through all of that, so the change in pressure, dP, is k dt times change in the density. And so as you rise up, this is negative. So the change in pressure is negative. Okay? And if you go through the math, what you can show is dN over NV. So the change in density over NV, again, a logarithmic change, is equal to that. So the density of molecules with y as a function of y is exponentially decreasing. Okay? And what's interesting is, see, this is m is the mass of a single molecule. This is the potential energy of a molecule, and that's kBT. That's related to the temperature. Okay? So, so higher the temperature, slower it would decay. Okay, so at about, if you put in the numbers, at about 8 kilometers, which is 5 miles, the number density at about 5 miles is, this is the sea level density times 1 times, so it's about 35% the sea level density. Okay. And so if you put in the numbers, well, Denver is 1 mile up, not 5 miles up. In Denver, the density of air is 80% the density of at Dayton Beach. Mount Everest is 9 kilometers up. So at the top of Mount Everest, the air density is 30% the density of sea level. Okay, and you know that people climb Mount Everest without oxygen. Okay. Now, here's a very interesting formula. This is potential energy, okay? And that's the temperature, okay? So you can think of this as the probability of an energy level being occupied. All right, so at a given temperature. So as the temperature rises, okay, as the temperature rises, higher energy levels can be occupied. Okay? So let's say if a system has 2 levels, okay, at low temperature you'll have more molecules here, and so at low temperatures this would be the case, and at a higher temperature you would excite more molecules there. Okay, so there'll be more molecules in the excited state. Okay. Now, so at infinite temperature, when the temperature is infinite, you can have equal number of molecules. You'll have equal number of molecules in all the states. Okay. For a laser, when you build a laser, what you have is essentially you have 2 levels. And for a laser to function, you need more molecules in the higher excited state than in this state. So what does this mean? If you look at it from a probabilistic perspective, that the probability of this occupation of this level is greater than the occupation of this level. How can you have higher probability for a higher energy level? If the temperature were negative, so you can think of this as this state being a negative temperature state. All right, so that's called a metastable state. So in a laser, what you do is, okay, so you excite an atom from here to there, which decays into this state, and this is a long-lived state, and so you can put more atoms there than here. And then when this de-excites, okay, all the photons are in phase. Okay, and that's a laser. Okay. So anyway, that's a negative energy state. Okay, you can think of it as a negative energy state. Okay, anyway, so that finishes.